Let us solve problem number 4. The problem states that an axial flow impulse steam turbine has a main diameter of 0.5 meter and runs at 3300 rpm. The speed ratio is 0.45 and the nozzle at the rotor inlet is 20° such that Vu1 is positive. The blade velocity coefficient is 0.91. Find A. The rotor blade angles at inlet and outlet, assuming 1. The condition for maximum utilization, 2. The blades are equiangular. B. The power output in each of the cases if the mass flow rate is 10 kg per second. C. The axial thrust in each case. First, let us list out the data given in the problem. So, the data are, they are given the mean diameter dm. Dm is 0.5 meters and the rotational speed of the run or the turbine is given, that is 3300 rpm. Then they have given us the speed ratio, which is denoted by phi, and that is 0.45. Then we have the nozzle angle at the rotor inlet, that is alpha 1, which is 20°, and the blade velocity coefficient, that is Cb, is given as 0.91. And now we have 3 parameters or 3 problems to be solved here. A, we need to find out the blade rotor blade angles, that is beta 1 and beta 2. To find out beta 1 and beta 2, they have given 2 conditions. The first condition is for epsilon max, that is maximum utilization factor, and the second condition is when the blades are equiangular, that is beta 1 is equal to beta 2. Here epsilon max condition will not be there for the second case. For the first case, beta 1 and beta 2 can be different or can be same, and then for that we need to find out the values of beta 1 and beta 2 for these 2 cases. Then B, we need to find out the power for both the cases, that is for condition 1 and condition 2. And then C, we need to find out the axial thrust, which is denoted by Fa, that is also for case 1 and case 2. So, these are the things which you have to calculate for both the cases. Now, let us find out the velocity required, that is u. So, u can be calculated with the help of these 2 data, that is mean diameter and the rotational speed, and to calculate V1 we have to use the speed ratio, that is phi. So, first let us calculate u. U will be equal to pi into dm into n divided by 60. Let us substitute the values. So, u will be equal to pi into mean diameter is 0.5 meters multiplied by the speed is 3300 rpm divided by 60. So, this gives us a value of 95 meter per second. So, u is 95 meter per second, and I know the speed ratio phi is given by u divided by V1, which is equal to 0.45, that is given in the data. So, from this I can write V1 will be equal to u divided by 0.45 and u is 95 divided by 0.45. So, this turns out to be V1 will be equal to 211.1 meter per second. So, now as we know that to construct any triangles we need 3 datas out of 6 datas in the triangle. So, now I have V1 and I have u, then I have alpha 1. So, these 3 datas are sufficient for me to construct the inlet velocity triangle. Then from here I know Cb, so that will help me to extend or construct the outlet velocity triangle. and I need to construct the velocity triangle for these two cases. So first we will construct the triangle for these two cases, and later we will go through uh, the required parameters to be calculated. So to construct the velocity triangle, I will go to next page. Here I will write all the required data first. So I need alpha 1. Alpha 1 is given as 20 degree. Then I need V1. V1 is 211.1 meter per second. Then U is 95 meter per second. Then CB is given. CB is 0.91. These are the data which are common for both the conditions, and I list out the conditions here. Condition 1 is for maximum utilization, which means to say that whenever we say the term maximum utilization, so V2 will be axial, which in turn says that alpha 2 will be equal to 90 degree and VU2 will be equal to 0. So when we are constructing the velocity triangle, we need to take this into account. Alpha 2 should be 90 degree and V2 should be axial, which also means that V2 will be equal to Vf2. This is for the first condition, and the second condition is beta 1 is equal to beta 2. So now we need to construct the velocity triangle for these two conditions, then we will measure the required parameters. So I will start with writing U. Now we need to choose a suitable scale, and always V1 will be the longest side in the case of an impulse turbines, whether it is steam turbine or a hydraulic turbine or a gas turbine. If it is an impulse turbine, V1 will be the longest side, and we will keep that length to approximately 10 centimeter. So by looking at the value of V1, I will take the scale. 1 centimeter is equal to 20 meter per second. If I take this scale, then the length of V1 will be equal to 10.56 centimeter, or approximately equal to 10.6 centimeter, because we cannot measure 0.56. Then the length of U will be equal to 4.75 centimeter, which can be approximated to 4.8 centimeter. So now I know these two lengths. Now let us construct the lines. So U is a line, a horizontal line of length 4.8. So from here I will draw a line for 4.8 centimeters. Now I know alpha 1. Alpha 1 is 20 degree. What I will do is I will take the protractor, I will place it here. Then I need to mark 20 degree over here. So it's 20 degrees here. So I will mark it here. Where the line, where the scale touches this point, I will keep it there and I will draw a straight line. I will not worry about the length. So once I have drawn the line here, then I will take the compass. I will fix the end of the compass here. Then now I know that V1 is 10.6 centimeter. So I will increase this length to 10.6 and then I will draw an arc. Once I have drawn the arc, now with the help of a straight line, I will join this point with U. So this is Vr1 and this is V1. Now I will complete the inlet velocity triangle by constructing a vertical line from here. So this completes the construction of inlet velocity triangle. Now I will name the parts. Now I need to, for the first condition, I need to satisfy that alpha 2 is 90 degree and V2 is axial. For that, what I will do is I will construct a vertical line from this point. From this end, I will draw a vertical line. Again, I will not worry about the distance or length of this line. Now I know that CB is given as 0.9, which means to say that CB is VR2 divided by VR1, which implies that now I need the length of VR2. For that, first I need to measure the length of VR1. So let us measure the length of VR1. For that, I will take the scale. VR1 is approximately around 6.3 centimeters. VR1 is 6.3 centimeter. Now I need VR2. VR2 can be written as CB into VR1, which is 0.91 into 6.3 centimeter. So the length of VR2, we get it as 5.73 centimeter. So I can approximate that as 5.7 centimeter. Now I will take the compass, I will place it over here, and I will reduce the length to 5.7 centimeters. Now I need to cut an arc here. So where this arc cuts the vertical line, that is VR2 line, from that point I will join U. So now this completes the construction of the outlet velocity triangle. Now let us name the parts. Now let us construct the second velocity triangle, or this velocity triangle for the second case. So here the only change is, instead of for epsilon max, we need to draw the triangle for beta 1 is equal to beta 2. For that purpose, first let us measure the angle of beta 1 and beta 2 from the first velocity triangle. I will keep the protractor here. Now we can see that the value of beta 1 is around 35 degree and the value of beta 2 is around 33 degree in this case. So now I can construct the velocity triangle for the second case. So what I have to do is, I need to change the angle of beta 2 to 35 degree. So what I will do is, I will mark that point. So for the second triangle I will be using yellow color. So from here I will measure 35 degree, which is here. Now I need to draw a line. So I will take the scale, I will place it here, and now I need to measure I will place the compass here. The length remains same. So I will cut an arc. Now with the help of straight line, here I will draw a vertical line. So there is a very slight change in the lengths of V2 and VR2. It approximately remains same. Now let us measure the lengths. I need to find out the power and axial thrust. So for that I need delta VU for both the cases and delta VF for both the cases. So let us measure those things. So before that, from here I will draw a vertical line. The distance from here till here will be delta VU for case 1. The distance from this line to this line will be our delta VU for the second case. Similarly, I need delta VF. For that I have to draw horizontal lines to measure the height difference. From here I will draw a line, and from here I will draw another line. Now this distance will give us delta VU for VF for second case, and this will give us delta Vf for first case. Now let us measure those values. I'll make the scale horizontal. Now if I measure from here till here, it is approximately 10 centimeter. So delta Vu for the first case is 10 centimeter. Now let us see for the second case. I have to measure from here. That is around 9.9 centimeter. So here it is 9.9 centimeter, and now we need to measure delta Vf. So I will make the scale vertical. If I measure this, the distance between these two will give me delta Vf for the second case, and that is approximately equal to 0.3 centimeter. So I will write it here. Delta Vu for the first case is 10 centimeter. Delta Vu for the second case is 9.9 centimeter. Now delta Vf for the second case, we are measuring for the second case, that is 0.3 centimeter, and if you measure it for the first case, I place the scale over this, it is 0.5 centimeter. So delta Vf for the first case is 0.5 centimeter. Now let us go back to the previous page and calculate the required parameters. Now we have these 4 values. I'll write those values again here. So now we have 3 different questions here. For question A, for condition 1, beta 1 was 35 degree and beta 2 was 33 degree. For the second condition, beta 1 was equal to beta 2 and that was 35 degree. Now B, we need to find out the power output for each of the cases. So B, here the mass flow rate is given as 10 kg per second. Now we need to find out the power output. So power for the first case will be equal to m dot into u into delta Vu for the first case. So if you remember, delta Vu for the first case was equal to 10 centimeter. If I write that in terms of in terms of meter per second, then that is 10 into 20, which is 200 meter per second. So the power output for the first case will be equal to mass flow rate is 10 kg, then U is 95 multiplied by 200 will give us 188.4 kilowatt. So this is the power for the first case. Now we need to find out the power for the second case. So the power for the second case is given by mass flow rate into U into delta Vu for the second case. We got delta Vu for the second case as 9.9 centimeter, which will be equal to 9.9 into 20, which is 198 meter per second. These two values are very close. So the power for the second case will be equal to 10 into 95 into 198, so which is equal to 188.1 kilowatt. So this is the power developed for the second case. Now we need to find out the axial thrust. So C, we need to find out the axial thrust. Axial thrust for the first case is given by m dot into delta Vf for the first case, and we know that delta Vf for the first case was 0.5 centimeter. If we convert that into meter per second, then that would be 10 meter per second. So, Fa will be equal to 10 into 10, which is 100 newtons. So, Fa for the first case or first condition. Fa for the second condition is given by m dot into delta Vf for the second condition, and from the diagram we know that delta Vf for the second condition is 0.3 centimeter. If we convert that into meter per second, then that is 6 meter per second. A for the second case will be equal to 10 into 6, that is 60 newtons. So, these are the required parameters. So, we have calculated the angles beta 1 and beta 2 for both the conditions. Then we have calculated the power for both the condition and the axial thrust for both the condition. This completes problem number 4. Now, let us solve problem number 5. Problem number 5 is for a two-stage impulse turbine. Let us go through the problem. The following data refers to a velocity compounded impulse steam turbine having two rows of moving blades and a fixed row between them. The velocity of steam leaving the nozzle is 1200 meter per second. Nozzle angle is 20 degree. Blade speed is 250 meter per second. Blade angle of the first row of moving blades are equiangular. Blade outlet angle of the fixed blade is 25 degree. Blade outlet angle of second moving row is 30 degree. Friction factor for all the row is 0.9. Draw the velocity diagram for a suitable scale and calculate the power developed, axial thrust, diagram efficiency for steam flow rate of 5000 kg per hour. So, here first let us write the data given in the problem. So, the data given are, he is saying that the following data refers to a velocity compounded impulse steam turbine having two rows of moving blades and a fixed row between them. So, we have two rows of moving blades. In between them we have a fixed blade which just directs or guides the steam to the next stage. Okay. The velocity of steam leaving the nozzle is 1200 meter per second, that is V1. V1 is 1200 meter per second, and then the nozzle angle, that is alpha 1, will be equal to 20 degree. Then the blade speed is 250 meter per second. The blade speed is u, which is 250 meter per second, which remains constant for both the stages. The blade angles of the first row of moving blades are equiangular. So, for the first row of moving blade, the blade angles are beta 1 and beta 2, and he says that those two are equiangular. So, they remain, they will be equal. Blade outlet angle of fixed blade is 25 degree. For a fixed blade, since there is no relative motion between the blade and the fluid, only the fluid will be moving and the blade is fixed. So, our frame of reference will be blade, and there will be no relative velocity term which comes into play. So, when we are dealing with fixed blade, those angles will be of the fluid. So, it is the fluid angle at the outlet of the fixed blade, and that will be our alpha 3. So, alpha 3 is given as 25 degree. Then the blade outlet angles of the second moving row is 30 degree. So, the blade outlet blade angles of the second moving row will be beta 3 and beta 4. So, the inlet blade angle will be beta 3 for the second stage, and outlet blade angle will be beta 4 for the second stage. Here he is stating that the blade outlet angle of the second moving row is 30 degree. So, the blade outlet angle is beta 4 for the second stage. Beta 4 is given as 30 degree. He has not given any value for beta 3. The friction factor for all the rows is 0.9. Cb for all the rows is 0.9. So, Cb for the first row of moving blades can be written as Vr2 divided by Vr1, which we have encountered, and for the fixed blade there will be friction between the stream and the fixed blade. So that also has to be considered, and that is given by V3 by V2, outlet velocity by inlet velocity. For a moving blade it will be relative velocity, and for a fixed blade it will be the absolute velocity. And for the last row of moving blade, the ratios will be Vr4, that is the outlet relative velocity of the stream for the second stage, divided by Vr3, which is the inlet relative velocity for the second stage. So Cb has to be used for all the cases, and then now we need to draw the velocity diagram for a suitable scale, and we need to calculate the power developed, the total power developed by combined stages, then the axial thrust, that is Fa, then the diagram efficiency, that is eta b, and all this has to be calculated for a mass flow rate of 5000 kg per hour. So this should be converted into kg per second. So to do that, I will divide 5000 by 3600 seconds per hour. So that will be equal to 1.389 kg per second. Now we have listed out all the data required. Now we need to construct the velocity triangle. For that, I will go to the next page and I will write down all the values again. So here V1 is 1200 meter per second, alpha 1 is 20 degree, U is 250 meter per second, beta 1 is equal to beta 2, alpha 3 is 25 degree, beta 4 is 30 degree, and Cb is 0.9. So these are the data given. Now we are dealing with two stage turbines, impulse turbine. So while constructing the velocity triangle, I have to split the sheet into two parts. In the upper part we will write the diagram for the first stage, and in the lower part we will write the diagram for the second stage. Now I need to construct the velocity triangle. For that, I need to select a suitable scale, and always V1 will be the longest side in the in an impulse turbine. So I will choose the scale in such a way that the length of V1 will be approximately equal to 10 centimeter. So here, by looking at the values, I can select a scale of 1 centimeter will be equal to 100 meter per second. That gives me a length of V1 as 12 centimeter and the length of U as 2.5 centimeters. Now I have all the ingredients to start the construction of velocity triangle. So I'll import the tools, I'll import the ruler, protractor and the compass. So I'll be needing these things to measure the values and draw the velocity triangle. In the upper half of the sheet, I'll keep the scale at the center and I'll start with the construction. U is 2.5 centimeter, so I need to draw a 2.5 centimeter line. So this is 2.5 centimeter line. Now I need to measure alpha 1. Alpha 1 is 20 degree, so I'll place the protractor here and I'll approximately measure 20 degree, which is here. I'll mark a point here. Now with the help of straight line, I'll draw a line from here which passes over the marking. Again, I'll not worry about the length of the line, and we have calculated the length of V1 as 12 centimeter. So I'll increase the length of the compass to 12 centimeter, then I'll cut an arc. So now I need to extend the V1 further. So from here I'll draw an extension line. From here I'll just draw an extension line. Now this is the end of V1. So from there I'll draw one more line to U. So this will be my VR1. Now I just need to complete the inlet velocity triangle for the first stage. So I'll draw a vertical line from this point and I'll extend this horizontal line. Now I'll name the Now I need to draw the outlet velocity triangle. For that, for the first stage, I know beta 1 is equal to beta 2. First, I need to measure the value of beta 1. Once I measure the value of beta 1, then I need to measure the length of VR1 because CB is given. So with the help of CB, I need to find out the length of VR2. You can see that beta 1 is approximately equal to 24 degree. So I'll write beta 1 as 24 degree, which is also equal to beta 2. So here from this side I'll measure 24 degree. This is 10, 20 and 24 somewhere here. Okay, now I have marked 24 degree. Then now I'll construct a straight line from here which passes over the marking. Again, I will not worry about the length. Now I need to measure the length of VR1. So for that purpose, I will place the scale here and then I will rotate it. So the length of VR1 is approximately equal to 9.6 centimeters. So the length of VR1 is approximately equal to 9.6 centimeter. So the length of VR2 will be equal to CB into VR1, that is 0.9 times of 9.6, which turns out to be 8.64 centimeter. So approximately I'll take it as 8.6 centimeter. Now I'll place the compass here. I'll reduce its length to 8.6 centimeter. Then I'll take the compass to the other side. Now I'll cut an arc here. So now with the help of straight line, I'll join this point with U here. This completes the construction of V2. Now I'll draw a vertical line and I'll extend this and I'll extend this. Now we have completed the construction of the outlet velocity triangle for the first stage. So this is our VR2, this is our V2 and this is VF2, and this angle will be our alpha 2 and this angle will be our beta 2. Beta 1 and beta 2 are same for the first stage. Now I need to draw the second stage velocity triangle. Now I need to draw the second stage velocity triangle. For that I need to extend U downwards. So from here I will draw a vertical line downward, and from this point I will draw a vertical line downwards. Now at a convenient distance I will draw U. As we know U remains same for both the triangles. So I have constructed U here. Now I need to draw V3. I know alpha 3 is given as 25 degree. So I will place the protractor here and I will measure 25 degree. So I will mark a point here at 25 degree. Then with the help of a straight line I will draw a line where that passes over the marking. Now I need the length of V3 and I know the value of CB. I know that CB is also equal to V3 by V2. So if I want the length of V3, I need to multiply CB with V2 length. So now I need to measure the length of V2. I will place the ruler here. Now the length is approximately 6.5 centimeters. So V2 is 6.5 centimeter. So V3 will be equal to 0.9 times of 6.5, which is approximately 5.85. So that can be approximated as 5.9 centimeter. Now I will take the compass, I will place it over this point. From here I will join U. This completes the construction of second stage velocity inlet velocity triangle. This is V3, this is VR3, and this is VF3. Now I know the relation between VR3 and VR4, and they have also given the value of beta 4. So first let us mark beta 4. Now I know that beta 4 is 90 degree, sorry, beta 4 is 30 degree. So here this is 30 degree. Now I will draw a straight line. Now I need to calculate the length. So to calculate the length, I need to measure the length of V3. So I will place the ruler here and I will rotate the ruler. I will make it parallel to V3, and here we can see that the length of V3 is approximately 3.7 centimeter. VR3 is approximately 3.7 centimeter. VR4 will be equal to 0.9 times of 3.7. So the length of VR4 will be equal to 3.3 centimeter. Now I will reduce the length to 3.3 centimeter. Now with the help of a straight line, I will join this. Now I will complete the construction of the outlet velocity triangle by drawing a vertical and a horizontal line. Now I need to find out the power and the axial thrust. For the power, I need delta Vu for stage 1 and delta Vu for stage 2. So to measure delta Vu for the first stage, I will draw vertical lines from here, and to measure delta Vf for the first stage, I will draw two horizontal lines from the apex of the inlet and outlet velocity triangle. Similarly, to measure the delta Vu for the second stage, I will draw two vertical lines from the apex of both the inlet and outlet velocity triangle, and I will draw horizontal lines from the apex of inlet and outlet velocity triangles. So this entire length from here till here, this is our delta Vu1, this is delta Vf1. Till now for single stage we were using delta Vu and delta Vf. Since here we have two stages, so this is the first stage velocity triangle and this is the second stage velocity triangle. I will be calling them as delta Vu1 and delta Vu2. So the horizontal distance between these two lines will be our delta Vu2 and the vertical distance between these two will be our delta Vf2. And now let us measure those things. The length of Vu1 will be equal to around 16.7 centimeter. I will place this over here. The length of Vu2 is around 6 centimeter. If I keep the scale here, then delta Vf1 is around 0.5 centimeter. I will keep the scale here. If you measure this height, it's around 0.6 centimeter. This is around 0.6 centimeter. Now we need to remember these values. With the help of these values, we will be calculating the required parameter. So I list out all those values here. I need delta VU1, I need delta VU2, I need delta VF1, and I need delta VF2. So delta VU1 was around 16.7 centimeter, delta VU2 was around 6 centimeter, delta VF1 was around 0.5 centimeter, and delta VF2 was around 0.6 centimeter. Let us just verify those values: 16.7, 0.5, 6 and 0.6. Okay, these values are correct. Now let us convert that into meter per second. So for that we will just multiply the scale. So when I multiply the scale here, delta VU1 will be 16.7 into 100. So it is 1670 meter per second, and delta VU2 will be equal to 6 into 100, which is 600 meter per second. Delta VF1 will be equal to 0.5 into 100, which is 50 meter per second, and delta VF2 will be equal to 0.6 into 100, which is 60 meter per second. Now we have these values. Now we need to calculate the required parameters. So the required parameters are the power. Power is given by m dot into u into delta VU1 plus delta VU2. So this will give us the power. So the mass flow rate here is 1.389 multiplied by u is given as 250 multiplied by 1670 plus 600, that is delta VU1 plus delta VU2. So we get the power as 788.25 kilowatt. So this is the power delivered by both the turbines. Now we need to find out the axial thrust. Again, axial thrust is the mass flow rate multiplied by the change in the velocity in the axial direction, and we have two stages. So I need to add those two together. So delta VF1 plus delta VF2. So the mass flow rate is 1.389 multiplied by delta VF1 is 50 plus delta VF2 is 60. So FA will be equal to 152.79 newtons. So this is the axial thrust. Now I need to find out the diagram efficiency. So here they haven't given the nozzle efficiency, so the diagram efficiency will be equal to the blade efficiency. And if you remember, for an impulse turbine, always the input will be equal to the kinetic energy of the fluid. So here we are dealing with energies. So it is V1 square by 2, that is the input kinetic energy, and the output energy is U into delta VU1 plus delta VU2. So this 2 can be written in the numerator. So I will just erase the 2 here and I will write it here. So the equation for the blade efficiency, or in this case the diagram efficiency, is 2 into U into delta VU1 plus delta VU2 divided by V1 square. Now let us substitute the values. So 2 into U is 250 multiplied by delta VU1 is 1670 plus delta VU2 is 600 divided by V1 is 1200 squared. So blade efficiency we will get it as 0.7882, or the blade efficiency can be, or the diagram efficiency can be written in terms of percent, that is 78.82%. So this is the efficiency of the blade or the diagram efficiency. This completes problem number 5. Now let us solve problem number 6. Problem number 6 states that the velocity of steam at the exit of the nozzle is 440 meter per second, which is compounded in an impulse turbine by passing successfully through moving, fixed, and finally through a second ring of moving blades. The tip angles of the moving blades throughout the turbine are 30°. Assuming a loss of 10% in velocity due to friction when the steam passes over the blade ring, find the velocity of moving blades in order to have a final discharge of steam as axial. Also determine the diagram efficiency. In this problem, he states that the steam coming out of the nozzle is 440 meter per second, that is V1. So let us list the data. V1 is given as 440 meter per second, and that is compounded in an impulse turbine. So it's a velocity compounded impulse turbine by passing successfully through a moving, then a fixed, and finally through another ring of moving blades. So the tip angles of moving blades, that is the blade angles, are given as 30° throughout the turbine. So beta 1 will be equal to beta 2, which is equal to beta 3, which is also equal to beta 4, and that will be 30°. Assuming a loss of 10%, he is saying that the loss will be 10% when the steam passes over the blade ring, which means to say that we consider these losses as CB. So CB will be equal to 1 minus 0.1, which is 0.9. So 90%, the relative velocity ratio will be 90%, or CB will be 90%. Now we need to find the velocity of moving blade, that is U. U has to be calculated to have a final discharge of steam as axial, which means to say that the final discharge from the second stage will be V4, and V4 should be axial, and alpha 4 should be 90°. For this given condition, now we need to construct the velocity triangle, and from that we need to find out the value of U. So till we complete the construction of velocity triangle, we will not get any value for U. So I will go to next page for the construction. Here I will list out the given data. V1 is given as 440 meter per second. Beta 1 is equal to beta 2, which is equal to beta 3, which is also equal to beta 4, and this is equal to 30°. CB, which is VR2 by VR1, which is also equal to V3 by V2, which is equal to VR4 divided by VR3, and that is given as 0.9. Now we have to construct the velocity triangle. Since we don't know the value of U, we cannot fix a scale now. So I'll assume the length of U as 3 centimeter. I'm just randomly assuming the length of U as 3 centimeter. Now I also have to satisfy the condition, which is alpha 4 as 90° and V4 should be equal to VF4. So to satisfy this condition, I'll start from the outlet velocity triangle of the second stage. So I'll start from outlet velocity triangle of second stage. So what I will do is, so at the bottom of the page, I will draw a horizontal line for U, which is for 3 centimeter, Now I need to satisfy the condition that V4 should be axial. So I will draw a vertical line here. Once I have drawn the vertical line, I know beta 4 is 30 degree. So I will place the protractor here and I will measure 30 degree. So 30 degree is here. I will just mark a point here. Now I will just draw a straight line from this end of U where it passes over the 30 degree marking. So this will be my VR4 and this is V4, which is also equal to VF4, and this angle will be our alpha 4 and this is beta 4. Now I need to move backward. So I know the length of, I can measure the length of VR4, and if I measure that, so I can see that the length of VR4 is 3.5 centimeter. I know CB is 0.9. So the relation which is equal to VR4 divided by VR3. So the length of VR3 will be equal to the length of VR4, that is 3.5 divided by CB, that is 0.9. 3.5 by 0.9 will be equal to 3.88. So I can write VR3 is approximately equal to 3.9 centimeter. Now what I will do is, I know the angle beta 3. So I will measure 30 degree here. I will place the protractor and I will measure 30 degree from this end. So the 30 degree is here. Now I will draw a straight line that passes through the marking from this end. From here I will draw a line which passes through the marking. Now I know the length of VR3 as 3.9. So I will take this compass, I will place it over here. I will reduce the length to 3.9 and now I will draw an arc. So where the arc cuts the VR3 line, so that will be the apex of the outlet velocity, the inlet velocity triangle for the second stage. So I will complete the construction of the velocity triangle. This is our V3, this is our VR3, and this is our VF3, and this angle will be beta 3 and this angle will be beta 4. This is U. Now I need to construct the inlet velocity triangle. For that, first what I have to do is I need to project U upward. So from here I will draw a vertical line and I will just extend this vertical line. Now I know where our U lies. So from this point I will draw a horizontal line. So this is the U for the inlet velocity triangle. This is our U. Now I need to start with the outlet of the first stage. So to construct the outlet velocity triangle, I know the relation between V3 and V2. So for that, first I need to measure the length of V3. The length of V3 is approximately 6.6 centimeter. So the length of V3 is approximately 6.6 centimeter. And I know the relation between V3 and V2. V3 by V2 will be equal to 0.9, or V2 will be equal to the length of V3, that is 6.6 divided by 0.9, which is 7.3 centimeter. Now I know this, but I don't know the angle alpha 2. alpha 2 is unknown. So I cannot draw a line and then cut arc, but I know beta 2. So what I will do is I will take the protractor and I will measure beta 2 as well as beta 1 at the same time. Beta 2 is 30 degree, beta 1 is also 30 degree. So I will just mark points here. So this is 30 degree, I will mark a point here, and here over 30 degree for beta 1 I will just mark a point. From the right end of V1 I will just draw a line which passes through our marking. Now I will take the compass, I will place it on the left end of V1 because I know the length of V2 as 7.3. So left end of U I will place this. Now I will increase the length to 7.3 centimeter. Then I will draw an arc here. So if I join this point where the arc cuts VR2 to the other end of U, then I will get V2. So from here I will join this, I will get V2 and I will complete the outlet velocity triangle of the first stage. So by drawing a vertical line here and extending this U towards left. So now I will name the velocity, this is VR2 and this is V2, this is VF2. So this angle will be our alpha 2 and this angle is beta 2. Now I need to construct the inlet velocity triangle of the first stage. For that I have marked 30 degree. So I will draw a line which passes through our marking. I will not bother with the length. Now I know the relation between VR2 and VR1. So for that purpose, first I will measure the length of VR1. So the length is approximately 9.7 centimeters. So VR2 is 9.7 centimeter. So with the relation of CB, VR1 will be equal to length of VR2, that is 9.7 divided by 0.9. So 9.7 by 0.9 will be equal to 10.77 centimeter. So the length of VR1 can be approximated as 10.8 centimeter. Now I'll take the protractor, I'll place it over here and I'll increase the length to 10.8 centimeters. Where the arc cuts our VR1 line, so I'll draw a line from here till there. This will be our V1. I'll complete the inlet velocity triangle by drawing a vertical line and a horizontal line. And now I'll name the velocities. This is our V1 and this angle will be our alpha 1. This is our VR1 and this angle will be our beta 1 and this is VF1. Now in the problem they haven't asked any angles, so I will close the protractor. Now we need to find out the diagram efficiency and the velocity of the blade. So we need diagram efficiency eta b. For that, we know that I need u as well as delta Vu1 and delta Vu2. We are not asked to find out the axial thrust, so I will not worry about that. Now I need the length of V1 to find out the scale, because I know the value of V1. Now if I know the length of V1, then I can find out the value of the scale ratio. So for that, I will place the scale here and I will rotate this to find out the length of V1. I will extend this. We can see that the length of V1 is approximately around 13.5 centimeters. So I will write it here. The length of V1 is around 13.5 centimeter, but the value of V1 is 440 meter per second. So if I divide 440 meter per second by 13.5, I'll get the scale ratio, which implies that the scale will be given by 440 meter per second divided by 13.5, which is 32.59 meter per second per centimeter on the velocity diagram. This is the scale, or I can write it in terms of 1 centimeter is equal to 32.59 meter per second. So now we had assumed a length of 3 centimeter for u. So the value of u will be equal to 32.59 into 3, which is 97.77 meter per second. Now let us measure the values of delta Vu1 and delta Vu2. For that purpose, I will draw a vertical line here as well as a vertical line here. I need the horizontal distance between these two vertical lines. Similarly, we have a vertical line here. I'll draw a vertical line here. I'll draw a vertical line here. So now we need to measure these distances. So I'll make the scale horizontal and I'll keep the scale here. And if I measure the length, then delta Vu1 is approximately equal to 17.8 centimeters. That is from here till here. This is our delta Vu1. Similarly, so this length will be our delta Vu2. From here till here, it is our delta Vu2, and delta Vu2 is equal to 6.4 centimeter. We need only these two values from the velocity triangle, and we have satisfied the condition that V4 should be axial. So alpha 4, if you measure here, it is 90 degree. So we have satisfied that condition. Now let me go back to the first page. So from the graph or velocity triangles, scale is 1 centimeter will be equal to 32.59 meter per second, and u is equal to 97.77 meter per second. That is one of the parameter. then delta Vu1 is equal to 17.8 centimeters, 17.8 centimeter, and if I write that in meter per second, it will be 17.8 into 32.59. So delta Vu1 will be equal to 580.1 meter per second, and delta Vu2 is equal to 6.4 centimeters, 6.4 centimeter, and if I multiply the scale, 6.4 multiplied by 32.59, so delta Vu2 will be equal to 208.57 meter per second. Now we can find out the diagram efficiency or the blade efficiency, which will be equal to 2 into U into delta Vu1 plus delta Vu2 divided by V1 square. Let us substitute the values. Eta B will be equal to 2 times of U is 97.77 multiplied by 580.1 plus 208.57, everything divided by V1 square. V1 is 440 whole squared. So we get the blade efficiency or the diagram efficiency as 0.7966, or it can be written as 79.66%. This is the efficiency of the blade or the diagram efficiency. So we have calculated U, that is one of the problem statement, and we have calculated the diagram efficiency. So this completes problem number 6.